that information in a 1D model. But I think the future is bright for this technique. I'm going to go out on a limb and say something crazy, but I think that we could do from sort of optical to maybe 5 microns. I think we can do all exoplanet spectroscopy in that wavelength range from the ground using this high resolution technique. And that we should spend our space telescope resources on things in the mid-infrared, or in the UV, or cosmology. Yeah, no, cosmology. Okay, I'll stop there.
Any questions?
This is going way back, but actually if you look at backscattered spectra, you get a very rich knowledge of the planet's surface. And you said just atmosphere.
Oh, well, when we're talking about gas things, we don't have a surface. But yes, sorry, you're right. And this is what people...
Well, eventually you want to
Eventually we want to take pictures of continents and oceans and dinosaurs walking around and all of that. And so looking at the backscatter, right, this is this whole technique of direct imaging and coronography and the star shade. Those are going to help get that. And that's one of the prime mission, the exoplanet mission goal for this next generation, this LUVOIR, large UV optical IR telescope is going to use that approach to look at the reflected light off of the surfaces of these planets. Yeah, it's a good point. Yeah.
Like, how well are we, like, how well will we be able to measure metalicities if we had arbitrarily large numbers of lines? Like, with the really broad wavelength coverage from CRIRES plus these other instruments, are we going to be able to significantly improve the distance metallicity?
In a perfect world, yeah, but then your information will saturate. And so what's actually going to happen is, let's say we take our crappy 1D model and the knobs are metallicity and CTO ratio and temperature. What's really going to happen is we're going to get to a point where there's additional physics that we're not including, that we're missing, like the fact that the line profile with altitude is going to Doppler shift because of the winds. And so I think when we start adding in many more lines and over broader wavelength ranges, what that means is we're going to have more information buckets that we're going to have to fill, which means we're going to have to add more. We're going to have to add more free parameters for the models that encapsulate that physics. So, but you're right. It's an interesting experiment. If you had a perfect model matched perfectly to the data, you know, it's going to be diminishing returns. I don't know exactly how many lines that information saturates at, though. But that's a good question.
I have a follow-up kind of. So you mentioned the winds of like the HRCCS line. So that also happens in the Earth's atmosphere. So I wonder what is the kind of, is there a resolution that will break down this method if like the caloric lines are moving too much and kind of steering?
I mean, I know this. So then you start getting into sort of like a kind of a broadband regime, and I would say anything less than an R of like 3,000 is where this cross-correlation technique won't work, because then you need to be able to disentangle, you need to be able to isolate the Doppler shift of the planet. So I would say anything higher than about an R of 30,000 or so should be able to do that. But then you lose information of the individual like lines themselves, like the water lines and the CO lines will start blending together. That's not as satisfactory.
Is there like an upper limit of the resolution?
An upper limit?
Yeah.
Oh, I was going the other direction.
Like the caloric lines are moving, right?
Yeah, it's going to be more of a broadening though. So I think the telluric lines are gonna broaden as opposed to like Doppler shift one direction or the other. So I don't think there would be a limit as you go towards higher resolution, but
The velocities are much smaller.
yeah, well that too. Yeah.
I mean, don't you have a problem in this respect of the higher the spectral resolving power, the fewer photons you collect per delta lambda? And at some point, don't you just run out of photons per delta lambda? I mean, there must be a turnover at which the information content goes to zero.
Yes. Right, so you're battling this SNR of the star is going to go as 1 over the resolving power. And this is going to go linearly with the resolving power. So in principle, those two terms kind of will cancel out, such that you don't, right, like in a perfect world, an R of 100,000 and an R of 200,000, you're just trading resolution for noise, right? And so you shouldn't have, in principle, you won't have a difference there. I would say you wouldn't want to go to such a high resolution that the number of photons you're getting on a detector would be, say, below the other annoying noise sources like read noise and stuff like that. But you're right; these two terms are gonna trade off because you are losing photons the narrower your bins get, but then you're making that back up through this. So I don't know where the turnover would be. I feel like 100,000 is a nice good number because it's got a bunch of zeros in it. But I think you're right. If you were to keep going, at what point would this break down?
I think we'll take our last question.
Oh yeah, if we have infinite, yeah, we just build, yeah.
We'll take our last question and then people can talk to Mike later if they have time. Yeah.
There's another issue with the new instruments that you showed that has a very broad coverage. This broad coverage comes in a price. The price is efficiency. I'm not sure that you actually gain anything in the case that you are actually trying to pinpoint a specific molecule and not build some kind of an application or an instrument that just is optimized for that specific band. So if you have several bands that you are targeting, it might be a smarter strategy instead of trying to cover everything, say let's bid for this, and this.
But a lot of these instruments, there's an instrument that's going to go on the MMT that's going to be able to do 1 to 5 microns in one shot continuously.
And the MMT?
Yeah.
Not that I know of.
And that's, I think you're on that, right, Dave?
I think that's the Aries upgrade.
Yeah, maps.
But there, I mean, just Mercedes and Sega you're working on, you should show them the test bed. They're working on this. Really exploring these ideas.
Okay, educate me. But yeah, I agree. And then like the CRIRES Plus upgrade, I know like the K-band, for instance, they aren't really losing anything. They're just kind of swapping out detectors and I think changing the spectrograph. So that like the wavelength range that you're getting in the K-band is broader. But yeah, you might have to observe several